Welcome everyone to Osmocom Developer Call. Today we will have a presentation about Gsm-R and the railway GSM and its difference to GSM. Yeah, so what is this talk about? It's about Gsm-R history and stakeholders and specifications to set the context, also the use cases a bit. And then it will look at the technical parts of Gsm-R and how it differentiates itself from classic GSM. The talk assumes there is already a good understanding of how GSM works, so it will not explain how GSM works. And sorry for that, but it's really focusing on the differences on the railway-specific parts of Gsm-R. So, well, first of all, Gsm-R, for those who have not heard it, well, the R is for railway, and it's a specific derivative of the GSM mobile communication system as is used globally in railway systems. So for what kind of communication is it used in those railway situations? There's a couple of key different types of communications. There is the classic one-to-one, point-to-point voice calls, normal circuit switched calls, as we know them in normal GSM in the public networks. There is something that is new to Gsm-R, which is one-to-N voice calls, which are called broadcast calls, meaning there's one source of voice information that then gets broadcast to any number of receivers all across the network. And then there is finally the N-to-M case, so-called group calls, where you have sort of a resemblance of push-to-talk radio using GSM. So only one person has talk permission, but then the voice from that one person or one user gets transmitted to all the recipients. Of course, well, okay, we look at the details later. There's also the use case for transmission of data for train control. Train control means basically where is a train, does it have permission to drive on a certain part of track or not, and that kind of communication happens between what's called the RBC, I have it on another slide, rail block controller or something like that. We will expand the acronyms shortly, and the train engine. So you could say that latter part is like a machine-to-machine communication, and the former part, the voice calls, is human interaction for users. Interestingly, there is no mandatory specification for SMS in Gsm-R, so it may be there in a network, but it's not required by the Gsm-R specifications. So, yeah, some acronyms that we will have in the slides, and there will of course be more acronyms below. That's one of the things that always hits you first when you look at a new set of specs or standardization bodies. So UIC is the International Union of Railways. ERTMS is the European Rail Traffic Management System. So UIC is an entity that is an international body of railway operators. And ERTMS is an European system for how rail traffic is managed. And within ERTMS, there is ETCS, the European Train Control System. And ETCS is then what, for example, runs on top of Gsm-R in this machine-to-machine use case. And RBC is the Radio Block Center. Yeah, that's basically some, well, center somewhere with railway controllers. So if we mention controller in the context of this slide of Gsm-R, it's not the base station controller or some like, how can I say, IT device that controls something, but it's actually a person that is in charge of controlling trains. And the radio block center is basically a location with person and IT equipment that then supports train management and traffic management use cases. So the stakeholders that are involved in Gsm-R, as I mentioned already, there's UIC, the International Union of Railways, was established in 1922 with 51 members from 29 countries. Today it's 208 members from five continents. basically almost everywhere where railways are, the operators tend to be members of UIC. The EC, the European Commission, has been driving the standardization between GSM-R. We will see shortly. There's also a GSM-R IG, an industry group. So the UIC represents the railway operators, and the GSM-R IG represents the equipment suppliers. And then also we have SEPT, the body of European Postal and Telecommunications Administration, that also played a role in GSM-R, at least initially. If we look at the history of GSM-R, we have some, I didn't check the exact dates, but before 1992 or until 1992, UIC requests an allocation of frequencies from SEPT for use in railway use cases. There was a question that was not decided yet whether to use Tetra or GSM on those frequencies for digital communication in railway, basically replacing the old analog VHF-based communication. GSM was winning at the time, which probably then was 92, as the big reason for going with GSM was it was already deployed. First real operational networks existed in 91, 92, as opposed to Tetra, which came a bit later. So the decision was to go with GSM. And in 92, then the EIREN, not sure how to pronounce it in English, project was started by the Railway Association, UIC, and the European Commission. And the goal was to specify requirements of railways for mobile networks. So basically, the railway operators had to get together and specify on a very high level what kind of requirements they would have for a cellular mobile network. The first actual specifications have then been released in 95. At which point then UIC has started the MORAIN project. These acronyms will be expanded in slides, I think, in the next couple of slides. And this MORAIN project then had to validate the specs that were created in IREN, and also develop more detailed technical specifications, in some cases together with ETSI and or 3GPP later on. And within MORAIN also, it was not just specification work, but a steering group of French, Italian, and German railways was put in place. And as part of the project, also 3 trial deployments of GSM-R were done, one in the Paris area, one I think in Frankfurt or so in Germany, and another one in Italy, I don't know where exactly. So 3 trial deployments with all parts of the network, from user equipment to radio access network to core network, to get first experience with this. Then in 97, a memorandum of understanding was created in UIC to stop investing in analog systems, but to switch to digital GSM-R, which was later then amended by an AOI, which is not the angle of arrival, as SDR folks would think, but it's the agreement of implementation. And in 2000, these projects have concluded, and basically, I mean, of course, there's continued work on the specs and improvements on new versions, but at that point, basically, they decided the initial mission was completed. So what kind of groups do we have involved today? It's basically the ERTMS/GSM-R group, which is divided in 3 groups. One is the ERIC, and anything starting with E in this context means European, as opposed to LTE, where everything starting with E means evolved. So ERIC is the European Railway Implementers Group, which is those railway companies that have signed this MOU and AOI. Then we have a functional group, which is not practicing functional programming language, functional programming, but it is the group in charge of maintaining the so-called FRS, the Functional Requirement Spec, which is the spec that EIREN originally created. And then there's the operators group, which maintains the SRS, the System Requirement Spec, which is those specs that the MORAIN project originally put in place. Large parts of those, so I think the FRS, for anyone reasonably technical, is not worth reading because it's so high level you will be bored. The SRS is interesting to read because it actually describes, well, which features of GSM or other relevant lower level specs are mandatory and which are optional, and basically what kind of requirements there are really on a technical level. There is also, maybe to go back there, I said this develop detailed technical specs. So a lot of the specs just sort of specify things that already existed before Gsm-R, but then some bits were actually added to GSM with railway-specific requirements, and that is then where ETSI was involved to actually get those part as the GSM specs as we know them. So in Gsm-R, there is not really anything. They don't have their own technical specs that really specify how a protocol works, but they really just summarize or refer to other specs and which clauses of which specs are used, and they got their changes upstream into GSM basically to make sure that GSM specs contain all the lower level bits that they need. So what kind of mobile station types do we have in this network? A mobile station is, of course, the terminology for phone or anything that user equipment that people have. First of all, there's the cab radio, which is a fixed installation, a device with fixed installation in the engine cab, mainly for voice communication of the engine driver in the car, in the train, in the engine of the train. It's typically like a 3U 19-inch subrack, so it's not like a small handheld device, and it has some kind of display or screen and buttons, so you can interact with it from the cab. The other larger device is the eDoor, the ETCS data-only radio, which is also a fixed installation in the engine and is exclusively used for this train control system. So it doesn't even need to support any voice calls because it's a pure data-only device. Then we also have the GP radios, general purpose radios, which is a normal mobile phone as we know it. And then there are so-called operational or shunting radios, which have some slightly different specs. And for each of those mobile station types, the SRS specifications list like what kind of features are mandatory and not, and they differ between those different terminals. Yeah, so that's basically on the user equipment side. In terms of frequencies, there is the so-called RGSM band. Note the difference between Gsm-R and Rgsm. So Gsm-R is the system and Rgsm is the band, like we have PGSM or EGSM or other bands. The frequencies are here. I'm not going to read it. It's just below the EGSM band. So the 900 megahertz EGSM band, and this band is mandatory to be supported by the equipment used for Gsm-R in the EU, not necessarily in other countries. Some countries, I think, at least according to the references I found, really only Germany have an ERGSM, which is the extended RGSM band, which adds another 3 megahertz of spectrum even below the RGSM band. That was needed due to high traffic density and the need for more resources at certain locations. There are other countries that use Gsm-R in normal bands, not related to railway GSM. For example, in China, it's some eGSM channels. In India, it's some channels in the primary GSM band. In Australia, even on 1800 megahertz. In the end, it doesn't really matter on which frequency you use it. Like in GSM, whether you use it in 850 or 900 or 1800 or 1900 megahertz, you have the same features and the same protocol. Everything's the same, it's just the frequency is different. Likewise here. I mean, the reason for having separate bands really only comes down to making sure that there's no other users or there's some interference, or to have a dedicated allocation for this use case because it's deemed more critical than maybe other use cases of public commercial networks. So what kind of tele services are specified in Gsm-R? Well, we have the voice calls, the classic circuit switch voice calls, unmodified as we know them. There's also circuit switch data, like in normal GSM. There's nothing different about circuit switch data in Gsm-R. They also use supplementary services. Particularly important is UUS1. That's the user-to-user signaling during call setup, where some additional messages can be sent during call setup. And USSD is also a mandatory service within Gsm-R, because it's used, we will get back later to that, when functional addressing is configured. Interestingly, optional is GPRS, eGPRS. I mean, it's not required. All of this works in the circuit switch domain. And as I mentioned, SMS is also optional. What I found interesting is that if you support SMS, then there's also a specification for, let's say, group SMS. So you can send, like, let's say, a mailing list for short messages where you send one message and it gets sent to an entire group of recipients. That is specified even on the protocol level, as far as I'm aware. So then we have these additional new GSM-R related services, which are sometimes called ASCI, not the American Standard Code for Information Interchange. There's one I less, so it's the Advanced Speech Call items, which are split up in VBS, the voice broadcast system. That's the one-to-N calls I mentioned before. Then there's VGCS, the voice group call system, the N2M voice call use case. We have user-to-user signaling, as I mentioned already. It's the supplementary service that's associated. And we have also what's called Emlpp, the enhanced multi-level precedence and preemption. I've seen that many cases in the specs and was always wondering what this is all about, because it's never used in any of the commercial GSM networks. But once I looked at Gsm-R, it was clear it was added for that. And this basically means that subscribers and/or their calls can be put into different priority classes, and the BTS, or the BSC rather, will preempt lower priority calls if higher priority calls come in and there's no resources available. A little bit like emergency calls work, but with different classes in this case. So let's have a bit of a look how the group and broadcast calls work on the radio interface, on the interface. They also use TCH traffic channels like normal voice calls in GSM. However, there's a new provision for unidirectional activation of traffic channels, which means that all the people who are listening to a call are using a traffic channel only in downlink direction. And all of the mobile stations within that BTS share that same TCH and time slot. So this way you can have very efficient group communication. Every group needs one traffic channel in a cell, and then all the listeners are basically assigned to that same channel. If you have a group that spans multiple BTSs, which of course is the normal case, then each BTS within that coverage area with at least one participant transmits the same downlink data. So you basically have one TCH per BTS used for such a group call, and not irrespective of how many subscribers within that BTS are part of that call. Then in the group call, I mean, in broadcast, it's unidirectional. It's relatively easy. And having those channels unidirectional, of course, also means that there is no SATCH in downlink, uplink, because there is no, there are no measurement reports by the phones. I mean, either they receive the call or they don't. Where Kevin is asking whether the time slots are synchronized between the BTSs, I think that's not specified. There are, however, performance requirements for handover specified in the SRS specifications. So it may be that you need to do that TS level synchronization to achieve the handover performance figures, but I'm not sure if that's the case. I don't think it's that strict. And we will get to that also in a minute. How does encryption work? Well, there's group keys. Let's delay that question till the end. Let's look at the normal use case first, or the basic use case. So in voice group calls, we of course have also uplink somehow, because in a group call, of course, one person talks, and then that is called a talker. So we have talkers and listeners in these ASCII channels. And a talker can request access by sending a reg in the uplink on this traffic channel, similar to a handover reg, you could say. And then one talker at a time gets allocated an uplink TCH, or rather the same TCH in uplink, I guess. So a voice from that talker can reach the network, and the network will then relay it in downlink to all the listeners on this or other cells. There is some related signaling required, of course, and that signaling works using a new channel, a logical channel on the downlink called the NCH, the notification channel, which steals one of your SDCCH4 or SDCCH8 on the CCH carrier. A little bit like CBCH works. If you use the cell broadcast channel, you also lose one of your SDCCHs, and if you use notification, you lose another one of those. And these notification channels act a bit like a shared assignment or shared access grant channel, you could say. So in the end, let's say a group call is started for a certain group. Groups are identified by a number. So let's say group number 2342. And the subscriptions are stored on a SIM card. So your SIM card knows which groups you are subscribed to and which not. And let's say the new group call on this group is started, then on the notification channel, there will be a notification message that basically has the group call reference and the channel description. So channel description is the normal channel description as we know it from GSM signaling. And then all the phones will, in unacknowledged mode, receive this notification messages and will basically activate the channel description, which then is the TCH of this group call or broadcast call. Yeah, so that's how it looks like on the radio interface. Mostly straightforward. If you think about the use case and you know GSM, then that's how you would implement it. I mean, it's logical, basically. So what kind of changes do you need to do to a GSM implementation if you want to add Gsm-R support? There is a need for unidirectional TCH, as we just discussed. Also, there's so-called talker and listener detection, which is this some special reg values in the uplink TCH. There's the notification channel in downlink support, and also there's a related RSL notification procedure where the BSC sends notification messages that then need to be enqueued to be transmitted on the NCH. But all in all, I think it's relatively minimal, the impact to have this group and broadcast call support in the BTS. There are many other changes in other parts of the network, but for that, it's relatively simple. So on the BSC level, it gets a bit more complicated. There is assignment requests and results and status for voice broadcast services, also for voice group call services. I think you need to generate those RSL notification messages, and also the BSCs have definitions of broadcast service areas that you need to manage and configure somehow. And then yeah, that's sort of the job. Of course, there's also the channel activation towards the BTS, where you then need to specify the unidirectional activation of channels, like a traffic channel in a specific case. But yeah, that's mostly the BSC side. On the media gateway, you will have to add something like AOIP circuit sharing, where you have, let's say, from the MSC to the BSC, there is one voice stream. And then the BSC needs to multiply that so that each of the BTSs within the coverage area gets one copy of that stream. So you need this kind of circuit sharing or duplication of audio streams. And the real logic really needs to happen in the MSC. There's these additional A interface procedures, and then there's new protocols, the BCC, the broadcast call control, and the GCC, the group call control, that get added and that have associated state machines and so on. There's also a bit in the HLR, I think it will be mentioned in one of the later slides, that you need to manage the so-called functional addresses, to which we will get shortly in one of the next couple of slides. So one other aspect is this Emlpp, the enhanced multi-level precedence and preemption. It is divided in priorities. It's quite interesting that they're like in order. So A is the top priority, followed by B, and then 0 to 4. Not sure why they couldn't use 0 to 6 in this example. A and B are not even used by Gsm-R, so those probably have been put in there in case you want to have police or something that has even a higher priority than railway. So reserved for that. And then 0 is used for railway emergency calls, which, by the way, railway emergency calls are different from normal emergency calls in GSM. So there's two types of railway emergency calls. One is related to normal train operation, and the other one is related to shunting, or in German, rangieren, for those here. And then 4 is used for classic one-to-one PTP calls, and then other services or calls can be used anywhere in between. I think 2 and 3 are used a lot for group calls, if I remember the specs correctly. And in case of overload, the BSC will preempt, basically kill any lower priority calls, so it can create capacity for higher priority calls that may come up. Okay, so that's all the voice part, which is nice and fine. Now let's get to the data part, the ETCS part. So the European Train Control System, as I mentioned, that's signaling between RBC and the train engine. And signaling in this context doesn't mean signaling in the context of cellular networks, but signaling in terms of railway operations. And that means, for example, the position of the train, and also permissions whether or not a train is permitted to enter a certain section of a track, for example. The position of the train, interestingly, is not identified by GPS, because if you know some larger railways, you know there's only like whatever 5 meters or so between two tracks. You cannot get that wrong. So the positioning works by so-called balise in the track. So you have like an RFID transponder in the track every whatever many meters. And when the train drives over this balise, it detects sort of where exactly it is on the track, and that information is sent over ETCS, over Gsm-R, to the RBC, so the RBC knows where the train is. There's something called ETCS level 2 and level 3, which uses a Gsm-R as the underlying transport mechanism, and it is the only internationally, inside Europe, the only international method of train control. The national railway companies all have their own legacy train control systems that are incompatible. So if a train goes from Germany to France or to Netherlands or whatever, from Poland to the Czech Republic or whatever you want to, combination of European countries you want to use, every country has its own legacy train control systems. And that becomes problematic for high-speed trains because the normal visible signals that may exist next to the track, they are positioned at a distance that only works for, I think, up to 100 kph or something like that. And if you have faster trains, a visible signal next to the track would be too late. The train could no longer stop. So you have to use one of these electronic train control systems, and the only one that is interoperable all across Europe is ETCS level 2 or 3, which is based on Gsm-R. And technically, you have this eDoor, the data-only radio installed in the engine, which has actually at least 2 mobile stations capable of Gsm-R for redundant connections. Each of those has a a separate connection to the RBC, or I think even to different RBCs for failover there. And traditionally, the transport channel on the GSM layer is the circuit switch data call with transparent asynchronous teleservice on top. The network is required to support 2.4, 4.8, and 9.6 kilobits of asynchronous transparent teleservice. I think in reality only 4.8 and 9.6 is used, but the requirement says even 2.4 must be supported by the network. Inside the CSD channel, so that's like a modem emulation over GSM, circuit switch data. Inside there is a layer called Euro Radio, very, how can I say, a very innovative name, as if there was no other form of radio in the European Union or in Europe. This layer is a protocol specified outside of the context of Gsm-R. I mean, Gsm-R just establishes this transparent bearer, and then Euro Radio is the application layer protocol on top of it. More recently, I think in 2015, the spec, I mean, no network, of course, is implemented in 2015. There's also a possibility of optionally Gsm-R supporting GPRS and Edge, and in that case, then instead of CSD calls, you have PDP contexts established by the EDOR, and a TCP connection is established on top of that to the RBC, and then the same Euro Radio layer is used inside there. So that recent addition was done as a capacity improvement, since Gsm-R capacity in this small band is becoming problematic as more and more trains are using it. This Euro Radio layer, for those who may be interested in that, has an additional crypto layer. So there's end-to-end encryption between RBC and the ETCS equipment on board of the train. So even if the crypto of GSM or GPRS is broken, then there's a separate layer of encryption with authentication and so on in the Euro Radio layer. In terms of encryption, by the way, Gsm-R has A51 as a mandatory requirement and A53 as an optional requirement. I don't think A50 or A52 are required anywhere in the specs. So if one wanted to add support for ETCS to OsmoCom, for example, then what kind of modifications would we have to do? Well, in libOsmo coding, we would need the convolutional coding for circuit switch data, which is quite interesting because I think in some cases the interleaving goes over 26 bursts, not just 8 bursts like in TCHH, but very, very long interleaving. In Osmo BTS, we would then have to do the de-interleaving and interleaving using libOsmo coding for convolutional code. The RSL channel mode for the unidirectional channels would need to be parsed and implemented, and also the RTP encapsulation and decapsulation, the not for unidirectional, RSL channel mode for circuit switch data, of course, and not for unidirectional. I mean, of course, they're not bidirectional TCH channels in CSD. And RTP encapsulation, decapsulation of the v.110 payload. So basically the transparent asynchronous data, how it's encoded in the on the UM interface. Then you have a rate adaptation function inside the BTS, which converts to v110, which gets put into RTP frames, and that also basically the user plane part needs to be implemented. On the BSC, we again have this channel mode encoding for circuit switch data calls, not just on the RSL, but also on the A interface. But so the MSC basically assigns a channel and says it's a certain circuit switch data mode, and we need to convert that to the right RSL bits and do the assignment on the A bit side. The media gateway and MGCP client, we would have to signal a CSD payload in the session description protocol that is included in the MGCP messages between media gateway and BSC. And in the MSC, it's the same basically as here with the media gateway, but in addition also the circuit switch data bearer types in layer 3 call control and the MNCC interface. And with those kind of changes, we would actually have support for this CSD ETCS requirement. And there is a chance we might start doing related work by the end of this year to support this in Osmocom. One other bit related to Gsm-R that doesn't exist in normal GSM is called functional and location-dependent addressing. In classic GSM, addresses as perceived by the user means phone numbers, MSISDNs, identify a given subscriber, which is nice for the normal use case. In railway networks, you often don't care about the person or who you're calling, but you want to talk to the conductor of a certain train or the catering of a certain train or the driver of a certain train. So there is a dialing plan that encodes the train number and the function within that train, or the cab number and the function within that, and so on. And then there's also location-based addressing. So if you're on a train, then you want to call, let's say, the manager of that train, and it's always the same number because you're on that train. And if you go on a different train, if the crew switches, of course, if you dial that number, you again get the manager of the train you're on, rather than having to know the exact number or having to swap SIM cards or anything like that. To register or deregister for those functions, a USSD-based mechanism is used that is specified. I haven't looked at it in detail, but it's some USSD application in the core network by which from the UE, the users can register or deregister as a function or enter the train number in which they are working right now. The HLR then stores the related functional addresses, so calls can be routed to those, and that's what I said. The HLR also needs a bit of extension in this context. Yeah, the numbering plan for Gsm-R looks like this. The prefixes of the calls. So you have first the prefix and then typically some identifier. So if you have 2 as a prefix, then you have, I think, a 5-digit train number, and then you have a 2-digit number of the function within that train. So if you know train number 33600 and you want to talk to the conductor, then you dial 2 plus the train number plus the function number for the conductor in the train. Similarly, you have other prefixes for other functions, such as group calls or broadcast calls. Those start with 50 or 51. And likewise also train controllers. So if you're on a train and you want to talk to the controller on the land side, the stationary side of the network, 7 is the prefix for talking, and then you have primary controller, secondary controller, and whatnot in the detailed numbering plans. SIM cards also have some modifications for Gsm-R. There are the so-called Moraine FFFIS. Actually, I think I skipped a slide there, or did I somehow forget about it? Wasn't there? Yes, here. Exactly, that slide I skipped. Yeah, the spec naming. So we have EIRENE, the European Integrated Radio Enhanced Network, which produces FRS, functional requirements specs, and SRS, system requirements spec. Both are each one document, and those are versions. So currently we have FRS 8.0 and SRS 16.0. And those are each one document, not too many pages. I think the 200 pages is the SRS 16.0 that defines sort of the technical specs for Gsm-R. And then within Moraine, the mobile radio for railway networks in Europe, we have many different specs. They're divided in 3 classes of specs, which I found extremely annoying because you have to count the number of Fs and really pay attention. So you have the FFFIS, the FIS, and the FFFS. I'm not going to go into the details of those. I don't really care. Just found it very peculiar. The Moraine FFFIS for Gsm-R SIM cards, that's like the name of the spec. They don't have easy numbers like in the GSM or 3GPP world. So if you look into that spec, then it will define sort of how a Gsm-R SIM looks like. It's a normal GSM SIM card, classic SIM, not a UICC, with DF GSM and DF Telecom. There's a couple of additional files, which are also, the files themselves are specified in the normal SIM specifications required for the advanced speech call items, like your group memberships, broadcast memberships, and what kind of priorities you are permitted to use. And then we have some additional files in an additional directory called df-eirene, which relates to functional numbers and shunting and Gsm-R operator selection and so on and so on. So yeah, it's really just a couple of additional files on a normal SIM card. Those files exist on the Sysmo USIM and Sysmo iSIM cards, in case anyone notices. The df-eirene I only detected recently, so it's not present on the Sysmo USIMs, but I plan to add them to the next version, just in case anyone wants to play with Gsm-R network or equipment. So what kind of requirements in terms of features does Gsm-R place on the RAN and on the core network specifically? Interestingly, RAN flex, I think, is mandatory, which means MSC pooling, which we have just implemented in Osmocom. That's nice. It's also interesting that ISUB and MAP are specified for roaming between networks. So roaming based on SIP-I, for example, or BICC would not be permitted. It must be classic ISUB for the call signaling. And if GPRS is supported, also some relatively modern features need to be supported, namely NAC, Network Assisted Cell Change, which we also already implemented in Osmocom. And also inter-PCU LLC forwarding is mandatory. That means if you switch between PCU, or if you hand over, that's not handover. If you have mobility between PCU coverage zones, then the old PCU must forward the pending not yet acknowledged LLC frames to the new PCU. So the new PCU can transmit it or retransmit to the UE or MS after it has switched. The connection of the controller equipment, that is, again, the person in charge of train control at an RBC is connected either via ISDN or via SIP. And interestingly, some DTMF tones like star, 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 or hash, hash, hash are used then to signal end or muting of calls. Which I find quite an interesting hack that you use in-band signaling on the on this land-based equipment to talk to the to signal to the core network, basically. The interface between the ETCS RBC, so the whatever is the software that takes care of all the signaling with the train engines, to Gsm-R is specified as an E1-based interface until today, even the latest specs. So there is no option for any other interface. So the Gsm-R network must expose E1 lines with Euro ISDN on them. And then in the B channels, there is v.110 data, and that is the interface, how it's handed over to this, whatever the software or device is that handles the signaling of the Euro radio and higher layers of ETCS. There's a question from Shinjo about does the traditional OOB signaling also work for end mute calls? If yes, then it looks like redundancy. Yeah, I didn't really look at the details. I think there's some explicit requirement that if you have an R99 call, you must not use the normal call end signaling, but you must use this DTMF-based method. I don't really know what is the reason behind that, and I haven't really studied it in detail. I think in the end, I mean, the train controllers that are in some office of the railway company, They are connected, of course, not over the radio interface, but connected over a wired interface, these days SIP, formerly ISDN, to the core network, and they use probably some relatively normal terminals, and you don't have the Gsm-R signaling available there, so they had to deal with whatever normal phone equipment can use. I don't know what's the history behind this. It's a bit weird. There's also roaming, of course, in Gsm-R. There's two types of roaming. One is international roaming between railway companies. It's interestingly relatively few roaming agreements. There's a list I could find from German railways, and for example, they don't even have roaming with Spain. They have it with Italy and with France and Netherlands, and I mean all the neighboring countries. But if you go further away inside Europe, then there is no roaming internationally. Probably trains don't go that far. I don't know operational details on that. There's also national roaming from Gsm-R to public GSM. Most countries, at least I think, have that. It's in case of coverage gaps in the Gsm-R network. So the Gsm-R terminals of the railway staff can roam into a national public network, and also probably for failover in case some BTS goes down somewhere. So German engines and/or drivers may not have to go that far away. Yeah, also Volte. Yeah, there's many problems, of course. That's correct in interoperability with different track widths and different voltage and different frequency and God knows what, different everything. A failure of standardization 100 years ago, I would say. Yeah, so for anyone interested in looking at more specs, this is the URL that has all the EIRENE and Moraine specs, no registration required, publicly available to anyone. There was a question about the security. Well, I'll leave that slide in case anyone wants to type that. It's some years since I last looked at the crypto and security for voice group and voice broadcast calls. It does exist, and there is some method based on shared group keys. But to be honest, I don't want to say more about it now because I think I'm wrong and I may be confusing details of Tetra with details of Gsm-R at this point after the number of years. So I cannot really say more about it other than that there is something specified. And with that, I'm through with what I wanted to present here. So now we have some time for questions on the record. Also later we will have time for questions off the record in case somebody wants to have them off the record.
You said that the user equipment for the controllers is a wired interface. So, I mean, this is, you said it's true for the humans, but is there some kind of aggregation described for the data interface to all the trains? Because there must be so many trains. Do they have, I don't know, hundreds of parallel ISDN channels carrying the data?
According to specs, yes, of course. I don't have operational insight into real-world networks, but the specs, and I just checked today the latest versions again, so I don't tell about stuff I read 10 years ago. So it is the case that it's an ISDN line, E1 line with 30 B channels, and not just every train, but every mobile station in the E-door of a train, of which there are at least two. So every train has at least two ISDN-P channels occupied on this E1 interfaces to the RBC. It's probably the single biggest remaining ISDN user out there. Kevin is asking how widespread is Gsm-R used. It's extremely widespread. It's used in Australia, in China, all over Europe, in many countries around the world. And you can read some figures. I think in France it's 9,000 kilometers of tracks. In the UK it's 14,000 kilometers of tracks with Gsm-R. It is the default way, and I think you have to consider that Gsm-R, I think, was first operational in 2005 or 2007 or so. So it was 17 years later than normal GSM. So basically everything gets shifted further in the past, into the future. As Alexander said, also Russia, yes, many countries and regions around the world use it. I think there is a requirement for all the equipment vendors to be able to supply Gsm-R until 2035 or something like that. So quite some time into the future. And it makes sense if you look at the normal technology cycles in the railway industry. It's an extremely long-lived industry. And after, probably 100 years or so of not having standards that allow trains to interoperate across different European countries, they finally have a standard, and I think it will take quite some time to switch to the successor. And yes, there is successors, as Alexander and Shinjo point out, FRMCS and so on, but I think it's going to be a long time until this is deployed, at least in Europe, and Gsm-R will stay for quite some time. Also in Europe, there are now many tracks where the only method of train control is based on Gsm-R. So there is no other alternative anymore. I think Switzerland has many tunnels where Gsm-R is the only control mechanism, and in Germany also a number of new high-speed tracks. Trials, of course. There are trials of modern systems and so on, but we are not at a point where there's any requirement, at least as far as I know, for any company to actually implement any of the successors at the moment. Germany is not very, doesn't have a lot of ETCS level 2, as Shinjo points out, yes, but there are other countries. I think UK, France, and Switzerland have a much higher ETCS density, ETCS level 2, which is the one that uses Gsm-R. Maybe one interesting bit also regarding the physical layer, I skipped that part, but of course high-speed trains, depending on where you are, really go quite high speed, which means you have more Doppler shift, and which means you have higher requirements on the equalizers in those handsets. So it's I don't know in detail, but it's imaginable that the equalizers and the physical layer processing of Gsm-R devices is a bit better than your average GSM device out there. The question about the vendor, it's an open market of equipment vendors. You can find, I think the English Wikipedia page on Gsm-R has a list. From Huawei to Nokia, Siemens to Kapsch to, I don't know, there's a number of different vendors. Some of them are identical to the civil base station and core network vendors, but some are really dedicated. For example, Kapsch from Austria, I think they only do Gsm-R and no other normal GSM devices. Alexander mentioned there's a special high-speed mode on the air interface, not in Gsm-R as far as I'm aware. It's the normal. It's just the specs. The specs basically have tighter performance requirements in terms of bit error rate and so on, and how you implement that with your physical layer is up to you. The MS antennas outside the train, I would hope so. I would hope so that they are installed. It's fixed installed for the cab radio and the e-door for sure, and this is fixed installed equipment, and they certainly have antennas outside the engine. But of course, the handheld devices that your conductor has inside the train is a normal handheld phone. It doesn't have an external antenna. Has anyone seen secondhand Gsm-R equipment on eBay or such? Yes, indeed. I think I also bought some. I also got some other Gsm-R equipment from a friendly supporter, let's say. I have a couple of different devices here. I've only played with one so far. It's sort of, I mean, unless you do the network side, there's only so much you can do with the user equipment. Also, maybe a quick reminder for those who may not know or may not remember. Also, with Osmocom BB phones, we can receive Gsm-R and we can camp on Gsm-R cells. Because the analog filters are, of course, the Gsm-R band is already outside the pass band, so you get a little bit of additional attenuation. But we can just instruct the RFIC to go to that frequency, and we can correctly decode. And if you do a CCCH scan, you see the notification channel, and you see the MCC and MNC of the Gsm-R networks and so on. Thanks, everyone. Take care. Happy hacking.